So here's Rob Porter from Sony in Europe is going to be talking about scalability and performance. So a lot of what he's basically going to be following on from a lot of the things that Brad was talking about. So I think you'll really enjoy this. Go ahead.
Yeah, so this is a talk on the scalability and performance of the IS-04 and IS-05 APIs and how the JTNM technical recommendation 1001-1 help. So as Brad mentioned earlier, IS-04 and IS-05 are the APIs that you can use developed by the AMWA to help you discover and register media nodes when you plug them into the network and to make connections between them. TR 1001-1 has been recently published by the JTNM, and this is a document to help people who want to set up broadcast deployments really make sure that all the equipment can very easily be configured automatically. So it mandates things like DHCP, DNSSD, IS-04 and IS-05, and make sure everything can work together on that network. So I'll start off by talking about the IS-04 and IS-05 APIs and give a brief summary of how they work. I'll then go on to the AMWA NMOS scalability study and why we set that up. I'll then talk about some of the results of the study, and finally talk about some best practice recommendations that we've made and how the JTNM TR 1001-1 helps with that. So starting with the APIs themselves. So the context of this is all a professional media network where you've got typically ST2110 flows going across that network. And that network's centered on a network switch that you can see in the middle there. The network infrastructure represented by that network switch could in fact be more than one network switch. It could be any architecture from a single monolithic switch to a multi-layer leaf-spine network. What we then have attached to the switch are a number of media nodes. So here we've got a couple of cameras and a couple of monitors. So a media node in NMOS terms is defined as a logical host connected to the network. And that logical host can host one or more blocks of functionality that are known as devices. And those devices themselves can contain a number of senders, receivers, sources, and flows. And all of these things you see in bold there are known as resources in NMOS terms. And they're all defined by the JTNM content model. So as an example, we have an IP-connected camera there. So that's represented as a single media node. Within that, it has one device, that one block of functionality. That includes both an audio sender and a video sender for the mic and the camera. Each of those senders would actually be associated with a source and a flow as well. So the source is where that data comes from. The flow is the representation of the data that the sender will make available on the network. It also has two receivers, so these could be two video return channels back to the camera. Another example could be an IP multi-viewer. In this case, this is a 3x3 multi-viewer, again represented as a single media node, but within that node we have 9 devices this time, one for each picture-in-picture within that multi-viewer, and each device has an audio receiver, a video receiver, and a metadata or ancillary data receiver. And then key to IS-04 is the registration and discovery system, the RDS. And this can comprise one or more registry instances, each of which includes a database storing all the registered resources on the network. The RDS also exposes 2 APIs, the registration API and the query API, and I'll go into those in a bit more detail in a short while. Finally, connected to this network, we have an NMOS client. So this is the control system for the network. It could be something like a broadcast controller or a routing panel, and it allows the connections between the media nodes to be set up. So moving on now to the IS-04 registration API. So when we first connect a media node to the network, it needs to let itself be known to the network, and it does that by attempting to find a registry and then register with it. So first of all, it tries to discover all the registration APIs that might be advertised on the network. And it's the job of the RDS to advertise itself on the network using DNS service discovery. So it can do this either using multicast service discovery, multicast DNS, or unicast DNS. With multicast, it would itself advertise itself on the network. With unicast, it would rely on a name server to do that, a DNS name server. Once the media nodes have discovered any registration APIs that are being advertised, they will then select the one with the highest priority, and then they will register themselves. First of all, they register the top-level node resource with that registry, and then they go on and register each of the sub-resources in turn, so all the devices, then all the senders, receivers, sources, and flows. Having done that, at the same time, they'll start to post regular heartbeats. And the heartbeat is a way of letting the registry know that the node is still on the network. So typically, it will send a heartbeat message every 5 seconds to the registry, and the registry will reply that it's received that message. As long as the registry receives a heartbeat within a certain expiry interval, which is typically set to 12 seconds, then it will keep that node registered on the network within the registry. Otherwise, it will expire the node from the registry, and this is a way of making sure that it's up to date with all the resources that are currently actually attached to the network. So what do the APIs actually look like in practice? Because we're going to be measuring the scalability of these sort of things. We need to know what they actually look like. Well, they're not actually that heavyweight. They're fairly lightweight. So the registration request over the registration API is a simple RESTful API. It's an HTTP post operation with a small amount of JSON data describing what that node is, the host name, some description, some details about the endpoints available on that node. And the registry will then respond also with a very small amount of data, just to say that the endpoint for that node has been created within the registry successfully. The heartbeats are even smaller. It's just a very small amount of information. Again, an HTTP post operation saying that that node is still alive on that network. And the registry will reply with a response saying OK, and with a timestamp, so that the node know that it's been listened to. So that's the way that the nodes stay registered on the registry. How does something like a broadcast controller find out what's available on the network? Well, it will use the IS-04 query API, and it's able to get a list of all the resources on the registry using that API. It can also, rather than constantly polling the registry in case there's any new devices, any new media nodes on there, it can subscribe to WebSocket notifications, and this will mean any changes on the registry get pushed to the client, to the broadcast controller, to get it an up-to-date list of everything that's currently on the RDS. So moving on now to making connections between media nodes. This is where IS-05 comes in. So everything up to now has been IS-04. IS-05 is for connection management, and it has only one API, the connection API, and this is between a client and a media node. So some of our media nodes are primarily senders, some of them are primarily receivers, and we want to be able to make connections between them. So the client would, first of all, use the sending node's connection API to make any changes that it wants to make to that sending node, and then get a transport file from the sender with all the information required to make the connection. It will then post that transport file to the receiver, to the receiver's node. The transport file is typically an SDP file, a session description protocol file, and it will contain information. If it was a video sender, for example, it would contain the format, the frame rate, and so on, so that the receiver can prepare itself to receive the data from the sender. Once it's done that, it will then send a message to the network to say it's ready to receive multicast data from the sender, typically using an IGMP join. And then packets will start to flow over the network from the sender to the receiver, and hopefully we get a picture on our monitor. In terms of the data that's actually going over the network in this case, the SDP files themselves I've highlighted here, also not much data at all. It's just some human-readable text with the format information and so on. So it's nothing too onerous going over the network. But what we want to do is really make sure this can behave itself at scale. So the NMOS scalability study was set up by the AMWA to really make sure that for very large networks comprising thousands and thousands of these NMOS nodes in a typical broadcast, such as you might find in a typical broadcast installation, can we still use these IS-04 and IS-05 APIs and have operations working quickly in a timely manner when we're doing thousands of these operations at once? So we set up the AMWA NMOS scalability study within the AMWA. Sony volunteered to lead this, but a lot of the AMWA community were involved in specifying requirements and feeding back on some of the tests that we proposed to do. We chose to use a virtualized network for this study because we're only testing the APIs. We're not testing the transport data, the media transport over the network. So we felt using a virtualized network was justified for this. And what we then did was we set up that virtualized network and made timing measurements of various IS-04 and IS-05 operations over the network at scale. So our virtualized network, we chose to use the Mininet open source software to set up our virtualized network. This allows us to simulate a large number of network endpoints within a VM. So typically we have a physical host computer that can run any OS, be it Windows, Linux, or Mac. And within that, we run our Mininet virtual machine, which is Linux-based. And with some basic scripting, we can set up a network of our choice within Mininet. It's very flexible. You can set up a network of any topology. You can include a network controller optionally. And each switch within the network, represented by the red dots here, you can have many, many different so-called Mininet hosts attached. The Mininet hosts are effectively lightweight containers that run within the virtual machine, and each container can run separate independent Linux processes, but they're separated. They each have their own separate virtual network interface card, or virtual NIC, and it's all based on the OVS switch software, which is used in some real switches as well. So it's fairly representative of real switch architecture. What we then do is, well, first we extended the Mininet scripting language to allow us to run NMOS processes within each of those hosts. And the NMOS processes we used, they could be any implementation, but mainly for the study we used our own Sony implementation, which is the NMOS CPP software. So this is open source software that's freely available to use under the Apache 2 license. Lots of other vendors are already using it. And you can find it on GitHub at that address at the bottom of the screen. And it comprises both a registry implementation and a node implementation. So we run our registry on one of the Mininet hosts, and then we run a series of nodes on all the other Mininet hosts. Then what we want to do is be able to log what's going on and make some timing measurements. So we take our log from our registry, and using Logstash, we feed it into an Elasticsearch database in real time, and that drives a Kibana dashboard, which will plot a graph of everything registering with our registry in real time, and we can get some nice graphs that show the results of our study. The physical host computer that we used was an HP Z820. It's a few years old now, but it's quite powerful. It's got two 8-core processors, and with 64 gig of RAM. For the virtual machine, we used 40 gig of RAM and 12 of those cores. So we threw quite a lot of power at it, but it can run on a smaller processor, but because we wanted to scale out to thousands and thousands of processors, we needed quite a good machine. So going on to some of the results now. So the first study we did was initial registration using IS-04. And we set up our mininet with somewhere between 100 and 2,500 nodes. And each of those included 6 resources, the node itself, and then one of each resource type, node, device, sender, receiver, source, and flow that I mentioned earlier. And then we then measured the total registration time for all of those to register with the network, with the registry. And what we found was that as the number of nodes increased, the amount of time to register increased linearly. And it's that linear relationship that's important, because what some people were concerned about was once you start getting more and more nodes, you get a kind of a bottleneck in the system, and it starts to go exponential, and then you're running into real problems. But the fact that we've got a linear response, and the 2,500 nodes there is actually 15,000 resources, all making separate API requests to register, that was really quite a good result for us. We then focused in on that 2,500 node result and looked at the pattern of registrations over time. And what we saw was this wasn't completely linear. So it took a little while for some of the nodes to start to register, and also at the end, it took a little while for the last few to get registered. Overall, the time was 3.5 minutes for those 15,000 resources, which isn't too bad, but we could do a bit better, we felt. And as I mentioned, we have that slow start and long tail. To study that further, we thought we'd look at a smaller number of nodes so that we could repeat the experiment many times without having to wait several minutes every time. So we went down to 750 nodes, and we saw we got the same kind of pattern. So again, total registration time was over 50 seconds for 750 nodes. And again, we had this slow start and long tail that I talked about. So delving into the behavior of the software a bit more, we found that the slow start was actually due to the DNSSD discovery of the registry when the nodes are first join the network. So what they have to do is they have to look out for MDNS advertisements of the registry on the network, and then a series of questions and answers between the node and the registry take place to make sure those DNS announcements are the right sort. And all of that happening really overloaded the registry with, in this case, 750 nodes all going through that process at the same time. So sometimes the registry didn't respond, and then the node would take a long time timing out before it tried again. So we found the timeout was ridiculously long by default using the Bonjour library that we were using. So we then turned it right down to something more in the region of the heartbeat interval, in fact. So we turned the timeout down to 5 seconds, and we found that that definitely helped things. Before I show you the result, though, looking at the long tail, this was a very similar problem, but this time with the actual HTTP requests. So this was the registration request itself. Also, the registry would get slightly overwhelmed by those, and some of them would time out without the node getting a response from the registry. And again, the retry interval was set far too long by default. So again, we turned that right down to 5 seconds. And the result of this was that we got no slow start and a much shorter tail there. And we found the overall registration time reduced from 50 seconds right down to under 30 seconds, so nearly halved. So the kind of recommendation here is if you're going to implement your own registry and node, make sure you optimize for things like this and study what's really happening. The next study we did was to look at the response to the network after a failure. So if we pull the plug on the registry, and then all the nodes, or some of the nodes deregister, how long will it be until everything's back up and running again? So again, we used our 750 node use case. They all registered with the registry. And then we virtually pulled the plug on our registry for 5 seconds. And you can do this in Mininet quite easily. And what we found was, even though 5 seconds was less than the registry expiry interval of 12 seconds, sometimes the registry didn't receive a heartbeat from a node for slightly more than 12 seconds. So just a few of the nodes actually became expired from the registry and had to re-register themselves. But everything was back up and running, and everything was fully registered again within 30 seconds. We then pulled the plug on the registry virtually for a slightly longer period, for 30 seconds. And this time, this well exceeds the 12-second registry expiry interval. So rightly, the registry deregistered or expired everything, all the nodes from the registry. And then once we'd virtually put the plug back in, it took a little while for all the nodes to rediscover the registry and register themselves again. And we found full recovery took 90 seconds this time, which isn't too bad. Ideally, we'd recommend some redundancy on the network so you have a backup registry as well. And that's what the next experiment is actually about. So in this case, we had 2 registries on the network for redundancy. So if one registry goes down, you still have a second registry. Again, we did our 750 nodes with 6 resources each. And we had replication between the 2 registries, so they're federated. So as soon as one registry is up and running, and the other one will start getting messages from it to populate itself with the first registry's registrations. The second registry may also get some of its own registrations. And that's what you see here with this second registry. It got a bump when it started getting registrations from the first registry, and then it went up fairly linearly until it was fully populated with the 750 nodes. But the good news was that with 2 registries, our total registration time actually halved from 30 seconds to 15 seconds. So multiple registries, not only good for redundancy, but good for improved registration time at startup. And the final experiments I'll talk about involve IS-05 connection management. But before you can start thinking about connecting things, the client, the broadcast controller, has to know about everything that's on the registry using the IS-04 query API, as I mentioned earlier. So to populate the kind of cross-point matrix on that client, we need to query the registry and get a list of all the registered resources. So to get the full 2,500 senders and 2,500 receivers, we found we could do this in less than 1 second with some optimization. And the optimization was really to make sure we're using the pagination feature within the query API to make sure we could get everything from the registry in a sensible amount of time. We then went on to making a number of connections between senders and receivers, and we selected 750 cross points at random from our 2,500 by 2,500 matrix, and had to do the IS-05 connection operations that I mentioned earlier. And this time it took less than 3 seconds to update all those cross points and make all those connections. And again, optimized API usage was important. Our initial result was much longer than that, but by using WebSockets and push notifications, we managed to get it down to less than 3 seconds. So now, finally, just to reiterate some of those best practice recommendations and say how the TR 1001-1 JTNM technical recommendation helps with that. First of all, obvious really, but TR 1001-1 mandates the use of IS-04 and IS-05. So use IS-04 and IS-05 across all the media nodes on your network to ensure interoperability. And if you're going to follow the technical recommendation, then you have to do that. We found that using clustered or federated registries improved performance. We got faster initial registration and better fault tolerance with redundancy. Multiple registries are very definitely supported in TR 1001-1. In fact, it says you can have 1 or more registries, so that's fine. So we definitely recommend doing that. On to the big ones now. So the TR 1001-1 actually has a system resource that you might have heard Brad talk about earlier. And this gives some system-wide information, such as PTP information, but it also distributes the heartbeat interval. So when nodes connect to the network, they can find the system resource, and they can get a common heartbeat interval to use. And using a common heartbeat interval across all the media nodes is important. For one thing, they have to be aligned with the registry expiry interval on the registry. Also, for our particular implementation, we found the heartbeat interval was very useful for guiding our choice of timeouts for DNS, SD, and HTTP. And finally, the recommended values in the IS-04 spec, 5 seconds for the heartbeat interval, 12 seconds for the registry expiry interval. We found they work very well in our experiments, but there's no harm in, rather than just using that as a default, to actually mandating that everything gets it from a system resource to be sure that everything's using the same heartbeat interval. So TR 1001-1 really helps by doing that. And then the final recommendation, I mentioned some problems due to the use of multicast DNS and timeouts. It's really much better to use unicast DNS. We found we got improved registration performance when we changed our simulation to do unicast DNS SD. It's also better for scalability. It's actually essential if you're going to have a layer 3 network rather than a layer 2 network. And multicast DNS will be deprecated from IS-04 in the future. So TR 1001-1 helps by mandating that unicast DNS SD is used. So all media nodes will have to query a central name server to find the registry on the network rather than the registry advertising itself using multicast DNS. Finally, if anyone would like to repeat any of these experiments or just look in more detail at how we did them, there's also a link to a paper we've written. You can look at the AMWA NMOS Scalability Study test environment, which is available on GitHub. Also, the open source software is available on GitHub on the Sony GitHub pages. And there's a registry and a node implementation there that everyone is free to use under the Apache 2 license. As I mentioned, we published this in a paper at the SMPTE annual technical conference. In fact, towards the end of last year, that paper is, SMPTE have very generously made that freely available on the IEEE Explore website, and you can have a look at that if you want to find out some more information. So finally, it just remains for me to thank you very much for listening. Particular thanks also to Gareth Sylvester Bradley, who led the team that did all these studies, and to the rest of the team back in the UK who helped to run the study. Thank you.
Rob, thank you very much.